All right, we're moving into chapter 8 here, section 1. Make sure before you look at this section that you look at that integral table that's attached there in Moodle. You're going to need it to be able to answer some of these questions. So section 1 is mostly going to be techniques that you guys should have already learned in either algebra or in Calc 1 and 271 here. To do them. And all section 1 is going to be for us is just going through a bunch of examples. There's no definitions or anything like that for this section. So we're just going to start off right away. So example 1. So here we're going to be looking at the integral from 3 to 5 of 2x minus 3, all divided by the square root of x squared minus 3x plus 1 dx. Okay, so if you have a question like this and you're trying to find the antiderivative of this on the inside, something that you guys should already be very familiar with is u substitution, and that's what we're going to be doing here. So we're going to substitute out a function and set it equal to u. In this case, we're going to use the inside of this bottom square root. The reason we're going to use that is because the derivative of that we have up top here. Anytime you have something that you can set to be the u and you have the derivative that will cancel out in the end, then do a u substitution. So here we're going to let the u be the x squared minus 3x plus 1, and then du is the derivative of this, 2x minus 3 dx. Then when I do my u substitution, this 2x minus 3 dx will cancel out and substitute to be the du. So now when we do the substitution, keep in mind that the integral limits are going to change. This would be in terms of u, although I haven't found out what that is, because usually I resubstitute out the u's back into x's in the end. 2x minus 3 dx, that's all going to substitute out to be the du. And then I still have the square root, but inside that square root, that x squared minus 3x plus 1 is going to become the u. Just to rewrite this a little bit, because that's a little bit difficult to think about, I usually like numerical exponents more than roots, so that's u to the negative 1/2 du. This we can find the antiderivative of. We raise the exponent up by 1 and then divide. Negative 1/2 is going to go up to positive 1/2, and dividing by 1/2 is the same thing as multiplying by 2. So this would have antiderivative 2 u to the 1/2, and then we would just substitute back in my u here. So instead of 2u to the 1/2, this is going to become 2, the substitution here, x squared minus 3x plus 1. I made a little oopsie, so I'm going to erase some stuff and re-record. I forgot that this should still be inside of a square root, right? So it's 2u to the 1/2. So it's that u all square root, the 2 on the outside from 5 to 3. All right, so if we plug the 5 in, we still have the 2 out in front, and then it's going to be the square root. Plugging 5 in for the x's, 5 squared is 25, minus 3 times 5, 15. 25 minus 15 is 10, plus the 1 is 11. And that's going to be minus 2 times plugging the 3 into here. 3 squared is 9, minus 9 is 0, plus the 1, so square root of 1. Or you can just write this as 2 root 11 minus 2. Good, so that's going to be our final answer for this question. All right, so that's just the first example, and again, that's something that you've already learned in the past, u substitution. I'm going to make a new page here, and this new page that I'm going to make is all going to be labeled techniques. So these are all the different techniques that you can use to solve integrals. The first technique is just a regular u substitution. We're going to look at a lot more techniques here in just a second. Okay, moving on to the next example. So next example here, example 2. We're going to look at the integral of dx over the square root of 8x minus x squared. Okay, you cannot do a u substitution for this one. If you did let the u be the inside of the square root here, the derivative would be 8 minus 2x, and we do not have an 8 minus 2x anywhere else in the integral to substitute back out. So we're going to have to try something different. And that something different that we're going to try is noticing that the denominator is a squared term and then a linear term. Anytime you have a squared term and a linear term together, what we can do is complete the square. All right, so I know this is probably something that you maybe saw back in Calc 1, maybe even in algebra class back in the day. If you haven't seen it, it's okay. I'm going to show you what to do here. So to complete the square, I'm going to rewrite this denominator with the squared term out in front and then the linear term next. To do completing the square, you have to have the coefficient on the x squared be a positive 1. So I'm going to factor out a negative 1 out of these two terms. Okay, now is the step that we can complete the square. Anytime you have the coefficient on the x squared term to be 1 and then whatever the linear term is, you're going to take the coefficient on the linear term, cut it in half, and then square it. So that negative sign is still on the outside. We're going to leave the x squared alone. We're going to leave the linear term alone. They're going to take that negative 8, cut it in half, which is negative 4, and then squaring that, which is positive 16. Now you cannot just tack on a positive 16 without also canceling it out, so I'm also going to put a negative 16 on there. The reason we're doing that is because these first three terms are now a perfect square trinomial and we could factor them. These first three terms we could factor into x minus 4 all squared. Double check to make sure that makes sense to you. We still have this negative 16 on the end and we're just kind of stuck with that. Okay, so the reason we're doing that is now we can kind of go back and think about this with this substitution. So going back to my integral now, it's going to be the integral. We still have dx up top, but then it's going to be the square root. I'm going to rearrange this a little bit. If you distribute the minus sign in, this is going to be negative, but then the 16 is going to be positive. So I'm going to write it as the positive 16 out in front and then negative that x minus 4 all squared term. Here is where I want you to have that integral table in Moodle. If you don't have that, pause the video and go get that integral table. If you look at number 18 on the integral table, number 18 on the integral table looks like this. The integral of dx over the square root of a squared minus x squared. This and what we have are very close. The only difference is that we have this x minus 4 instead of this x squared. We can make our integral look like this integral by doing a u substitution. If I let u be that x minus 4, then du would just be dx. And then when I substitute that in, it's going to be the integral of du over the square root of 16 minus u squared. And now it looks exactly like number 18 on the table, just with u's instead of x's. So in this case, my a, you have to be a little bit careful here because that's squared. So really my a is going to be 4. And then from the table, the x is going to be u. If you look on the table, it gives you the antiderivative for this. The antiderivative for this is sine inverse of x over a plus c, which means that our integral here is going to have antiderivative of sine inverse u over 4 plus c. Do not forget to resubstitute out the u though, so our final answer is sine inverse of x minus 4 all over 4 plus c. So you will need to be able to use that integral table that I gave you in Moodle here. It's also in the book on page 448. So we use the u substitution from before and then also an integral table to get the final answer here. But notice how cool this is, or it's cool to me. We started with an integral that only had polynomials in it and a weird square root. Somehow the antiderivative of this came out to be a trig function, an inverse trig function at that. So just notice that as we move forward, that these are going to be kind of complicated and they're going to look kind of ugly. All right, so going back over to my techniques page, we have our second technique, and our second technique is just going to be that integral table. Always have that integral table with you. In fact, I would look over it before you do an integral because you want to look for patterns and you want to look for ways of just using the integral table instead of having to go through a whole process. Let's do one more example in this video and then I'll make another video with more examples. This next one should be pretty fast. So this will be the integral of cosine x sine 2x plus sine x cosine 2x, all with a dx. Okay, whenever you have trig stuff in the integral itself, we can do the antiderivatives for most of them fairly easy, but when you have one that's really complicated like this, it's going to be a little bit harder. Also on Moodle, I'm going to put up a trig identity sheet. I also want you to have that trig identity sheet with you whenever you go to take tests or work on the homework. The identity that we have here is going to be one of the addition formula identities. And so it's this one that we're using. So we're going to be using the trig identity. Sine, I think it's sine, let me double check. Yeah, sine of A plus B is equal to sine A cosine B plus cosine A sine B. All right, so that's the trig identity that we're going to be using. The right-hand side of the trig identity is what we have in our integral, and we're going to replace that with the left-hand side of the identity. Where for us, our A looks like that's going to be 2x. Our B is going to be x. That matches over here, right? B is x, A is 2x. So that means that we're going to substitute out my integral to be the integral of just sine of the x plus 2x, so sine of 3x dx. This should be an integral that you know how to do. Go back to Calc 1 if you don't remember. Also remember I have that Calc 1 homework assignment that you can practice with. It has some of these in there. To do the antiderivative of a cosine or a sine with a coefficient on the inside, you divide by that coefficient or do the reciprocal of the coefficient out in front. Then you do the antiderivative. The antiderivative of sine is a negative cosine, and then you leave the inside alone, plus c. And then just to simplify it down a little bit, we get negative 1/3 cosine 3x plus c as our final antiderivative for this complicated looking thing up here. Okay, pausing the video here. I'll see you in the next video with some more techniques. Oh, yep, that just reminded me. Need to add another technique thing to my techniques page. Trig identities is something that you're going to have to use as well. Okay, see you in the next